Okay, today we're going to have a little look at the history of the discovery of the structure of the atom. So, way back in the time of the ancient Greeks, in 450 BC, Democritus suggested that everything was made up of tiny invisible particles that he called atoms. This was not a popular idea at the time. And it took until 1803 for the idea to be popularized by John Dalton, when he said all elements were made of these tiny little particles that were indivisible, that you couldn't get anything smaller than these tiny particles, which he called atoms. However, in 1896, J.J. Thomson discovered the electron, and he discovered that the electrons were part of the atom. So the atom was not the tiniest, was not a fundamental particle. It wasn't indivisible. And this was quite a profound discovery. From this, he developed the idea of the atomic model based on what he called a plum pudding. So a plum pudding is a Victorian kind of cakey dessert thing. It would be served at Christmas time. And it would be a cake, rich fruit, so impregnated with all these different fruits with them, like dried plums, dried raisins. And so the idea is you've got this kind of cake with these plums or raisins within it, so that it'd be a picture of the atom with all these other little electrons dotted throughout the structure. That is the plum pudding model. This is wrong, and it was discovered in 1909, so it didn't take long for at this point in science, things are moving very, very quickly with the advent of the quantum discoveries. We've got Einstein working, you've got a lot of major discoveries coming one after the other. And one of them was the experiment by Ernest Rutherford in 1909. It's called the gold foil experiment, and he discovered that the atom is almost empty. So if we look at these, this is the idea of the plum pudding. So you've got this kind of just mass with these negative electrons throughout it. This is the idea that Rutherford came up with. So you've got this positive mass. So they knew if the electron is to be neutral, so it's not charged, they know it's got electrons which are negatively charged. There must be something that is positively charged to counterbalance. Otherwise, you're going to just have a negatively charged atom. So there has to be this positive mass in the middle, and then the electrons are all kind of dotted around this positive charge. This was the model that Rutherford came up with after he did his gold foil experiment. And we're going to have a look at that in a little bit more detail in a moment. 1911, so not long after, Niels Bohr refines this model. And he suggests that the electrons, they're not just floating about freely around this nucleus, that they can only be at certain levels around the nucleus. And these correspond to the energy of the electrons. Schrödinger refines Niels Bohr's model even more. He says, well, yes, they can only take defined energies, but we can't really tell where they are going to be. That the idea of pinpointing the location of an electron isn't correct. That we can only think of the location in terms of a probability. So this idea of energy levels gets replaced by orbital clouds, where there is a region where there is a probability of an electron existing. And within that probability, the electron can only take on that certain energy. So this is more the kind of Schrödinger model, and this has actually been proven. We can model these things. We can use we can image the different structures of an atom and the electron clouds or orbitals where these electrons have a probability of existing. So let us look more closely at the Rutherford scattering. So we're going to use the PhET website. So this has been put together by the Colorado University, and it is fantastic. It does all the sciences and mathematics, and it's a really good place just to go and play with different ideas in science. And they have simulations across grade levels. It is a really great resource. So we're going to look at the plum pudding model first. So what Rutherford did was he had this thin sheet of gold foil, and he had a source that made alpha particles. So an alpha particle is just basically a helium nucleus, 2 protons and 2 neutrons, and he fired his alpha particles at the gold foil. And this is what he expected to happen. He expected them just to fire right through. They didn't do that. This is what they did. So we'll go into the Rutherford model, turn it on again, and we can see that these atoms, these alpha particles, are not going right through our gold foil. They are being deflected off. Now, if you look at the scale down the bottom, it says 6 times 10 to the negative 5 meters. So this is the kind of scale of the diameter of 2 atoms. Let's go down to a smaller scale. So now we're at a scale of 1.5 times 10 to the minus 13 meters. This is the nuclear scale. This is the atomic scale. This is the nuclear scale. And this is now the nucleus of this gold atom. And you can see these positively charged alpha particles, as they get close to the very positively charged nucleus, they get deflected away because positive charges, like charges, will repel each other. So the positive alpha particles get repelled away from the positive nucleus. So this is what's happening at this nuclear scale, and we can see the effect on the atomic scale. And now we can see that when Rutherford conducted the experiment, most of them do go right through because most of the atom is empty space. But then you'll get this one, like these ones here, they're getting deflected off. That one gets very deflected off. Some of them, if you watch close enough, for long enough, that one got shot right back, almost the way it came, and some came right back and almost hit Rutherford in the face. And this was the scattering of these alpha particles in all these different directions was so different from what he expected. He understood that there was something fundamentally different with the atomic structure, and this is why he came up with his model for the atomic structure, which was, we've seen from what Niels Bohr then came up with, and Schrodinger wasn't quite right, but it was on the right track to being correct. And it was this experiment that opened up that whole new area of physics. Thank you for listening.